So, anyways, today's lesson is about enthalpy of solution and hydration in AQA-A2s, right? Uh, enthalpy of enthalpy of solution and hydration. What about the weather in that? You are now in Dubai, right? What's the weather? You are in India. So where are you right now? South India. Gujarat. What about the temperature and all? You are also getting the El Nino conditions, the hot weather and all, or what? Northern India, I am. Yeah, okay. It's raining. Okay, here it's kind of different. We are not getting much rain, and it's like yeah, we are under the heat wave. So at the moment, it's also like I think I don't have a thermometer with me. I think must be around like 36, 38, something like that. So good for you. So you have anyone in Gujarat? The your uncle. So you not from South India? You are from North India, even though you are living in North South India. So Gujarat is famous for lions, I guess, right? Lions and what else? Gujarat lions, and also your president is from also Gujarat, I guess. Am I correct? Modi. Yeah. Oh my God, you don't know. Oh my God. You are not living in India much. Right? Anyways, not a big fan of Modi. Really? Okay. It's kind of extreme to a level, right? I guess I heard like that. Anyways, let me start. Um, Solution of hydration, right? With the under solution of hydration, enthalpy of solution. Can you tell me what you know of enthalpy of solution? Yeah, what do you know about enthalpy of solution? Have you heard about it before? Mhm. Yes, so just like all the enthalpies, we got to learn two more enthalpies, some definitions of two more enthalpies. So after that, we are okay. The remaining two is about standard enthalpy of solution. The symbol is given as delta H solution, right? This is the standard, right? The moment node comes, it becomes the standard temperature and pressure, right? Standard temperature and pressure is standard, right? So shall we write the definition then? The enthalpy change, you don't need to memorize these things, right? Enthalpy change when one mole of an ionic substance, ionic substance are most of the ionic substance are getting dissolved, except there are some exceptions like barium sulfate. Enthalpy change when one mole, it is always given respect to a one mole. Either side, it could be either side of the equation, could be the reactant, could be the product, right? When one mole of underlying an ionic substance, an ionic substance. Example, sodium chloride, magnesium chloride, not barium sulfate. Barium sulfate is not getting dissolved. Magnesium hydroxide is also sparingly soluble, right? Enthalpy change when one mole of an ionic substance dissolves, right? But the next one is more important. In sufficient water, remember, right? Sometimes if you add only a drop of water to one mole of this ionic solid, will it get dissolved? No. Must add sufficient water. Excess water is, yeah, that is also good, right? Sufficient water or excess water. But I would say sufficient water is more clear. Until it is getting dissolved when we add it. Sufficient means that. Okay, until it gets dissolved. But if you just add a pinch of water, a drop of water, it won't happen like that. Substance dissolves in sufficient water. So they are always in the marking scheme. They are looking at these points, right? Sufficient water, underline, to form a infinite dilute solution. That term is also very important. Infinite dilute, right? It also has a meaning. To form an, what does it mean? To form an infinite dilute solution, right? Infinitely dilute. What does it mean? What do you mean by infinite dilute? What does it mean? Infinite dilute means, in other terms, very, very dilute, right? Very dilute, right? Very dilute means, in other terms, what about the concentration? Very, very low. Right? Sometimes you can't even tell how the concentration. It is going to be very dilute, right? Very dilute. Concentration is very, very low. Very, very low concentration. Very low concentration. Why this concentration matters, right? Why? So later you are learning about that physical chemistry. Solubility product constant. We are learning something like that. Why the concentration matters? In that part you will learn, right? To dissolve a ionic substance, to each and every ionic substance, there are some specific concentration is needed to dissolve it, right? And if you exceed that concentration, it is again becoming a what? Precipitate. For example, when you are making tea, right? For example, everyone likes sugar, right? So what do you do when you are making tea? You want to make it more sweeter. What do you do then? Yes, I lots of sugar, lots of sugar, lots of sugar, lots of sugar, and finally, when you are drinking, what do you get? It's sweeter. What? Sweet stays, but the thing at the bottom you may see some kind of what? A sugary syrup, solid, a sugary paste you can see, right? Have you seen that? Why? So the thing is, so in any solution, right, for any substance, there's a limiting concentration. If you exceed that concentration, just because you add more, it is not getting dissolved. Not getting dissolved, right? You add more and more and more, but the thing is, it is not getting dissolved. The excess is getting precipitated. It is not getting dissolved, right? In other terms, this solution contains, let's say, water. It should be able to bear the weight of this compound that we are dissolving. It also has a capacity. Now, if you exceed the capacity, what happens? The excess is getting precipitated, right? So later we are learning, so you don't need to write these things. At a particular temperature, every substance is having a specific value, a constant value. We are calling it as KSP, solubility product constant. It comes under physical chemistry. So no matter what, how much you are going to add, it is not getting dissolved, right? So that is why we have to make sure, right? So if it is not getting dissolved, for example, you are adding more sugar. Now you know now it is not getting dissolved. You are adding excess sugar. To dissolve this excess sugar, what do you do then? Practically add more water. When you add more water, what happens? More volume means more and more getting diluted. Again, the concentration drops. So completely it is getting dissolved. That is why we are going to do here also. That is why sufficient water means until it gets dissolved. Otherwise, you are having 1 mole, but only a certain part of that 1 mole is dissolved. So therefore, you are going to get a less heat change. Why? We are expecting the complete 1 mole to get dissolved, but only a certain percentage is getting dissolved because you are not adding sufficient water, right? So what we do is we add in excess water as you said until it gets in completely dissolved. So we make sure it is infinite dilute, right? Very dilute, right? Otherwise, you will not get the expected energy change. Energy change means enthalpy change or energy change per mole. That is called enthalpy. Is it clear? That is why all these definition matters, right? Do not take away anything. Infinitely sufficient, sufficient water, infinite dilute solution. All it matters a lot. Otherwise, it won't. It will not serve the purpose. Okay. Right. Right. We'll move on to the next slide. Uh, Now, remember we are using that aqueous symbol. Be careful of the aqueous symbol, right? You must write because we are making a solution. Aqueous symbol, make sure to write on the correct side for the correct products, right? And the other thing is, okay, can you write the equation for the enthalpy equation for dissolving or the enthalpy of solution for potassium chloride? Can you write the equation for delta H naught for what? KCl solid. For KCl. And then uh, for right magnesium sulfate, delta H naught, magnesium sulfate. Then for delta H naught, aluminium chloride. You can write the equation in two different ways. Same thing, right? In two different ways you can do. And while you are doing it, I am going to ask another question. Is it an exothermic or endothermic reaction? What do you, how do you assume? For example, neutralization enthalpy we discussed, it is always exothermic. Right? There are certain things, certain reactions, enthalpies. It is always exothermic, always endothermic. What about this one? Is it going to be endothermic or exothermic? While you are doing it, can you think and tell me? We discussed lattice enthalpy. Standard lattice enthalpy is always what? Exothermic, right? What about this one? Standard formation enthalpy of elements in the standard states, it is always zero, right? What about this? Later we are moving on to very interesting lesson. My favorite entropy, Gibbs free energy and the reaction feasibility. One of my favorite topics. Sorry, aluminium chloride. My bad. Aluminium chloride. Can you send your answers? Let me check. Okay. Oh, it's getting loaded. Give me a second. So I should have some confidence, right? Yeah, I know you are a very smart kid, right? You are so good. Last week we had to. Yeah, we are planning on having like 2, 3 classes, right, per week. So I think tomorrow also we can meet, I guess. Are you available? I don't know. Yeah, same time we'll try to see because my vacation ends like in 3 weeks time. So before that we can have classes actually. Yeah, I have you on. Okay, let me check. Can you see the screen? Uh, right. So in your answer, uh, so why you are writing it as we are going to dissolve ionic solid, right? So okay, KCl solid. So when you dissolve it in aqueous medium, what do you get? You are adding water. Water means ice aqueous. You should show it right in the equation. Okay, you are adding water plus aqueous. What do you get? You are getting ions, right? Potassium plus ions. What else? Cl minus ions. Or you can write it this way also. Both together, right? Because you don't have it together I mean, in a solution, but you can write it like this also. It means the same thing. Or like this. Here also, what is this? Magnesium sulfate. Then what should be written here? Now this step is wrong, right? You can't have magnesium solid. You have ions here, right? In the ionic lattice. Understood? Do not overcomplicate it, right? Very easy stuff. What you did in all levels. Nothing else. Magnesium sulfate. You must show that you are adding water, aqueous, lacking water. You get magnesium 2 plus ions and what else? SO4 2 minus. Now I want you to fix this. Aluminium chloride. Is it correct? Is the formula correct? AlCl3. Sorry. Then what should be written here? Al3 plus. Or can you fix it as any the answer? Right. So this time H2O liquid, my advice, and don't write as H2O. But if you write it as H2O, there's an issue with balancing it. How do you balance it? Right? Now, if you write your answer like this for this one, so remember it is an equation. Both left hand side and right hand side should be equal. Atoms, number of atoms. Right? Now, if you are writing it like this, the issue is what? How do you balance it? Ah, that is the case. Then what? The whole principle under chemistry is going to fail. Keep that in mind. Always it works under concept. We just can't add atoms or molecules to either side. It always governs a certain law. Right? Remember, this is science, right? Always be careful. Okay? So if you write like this, it's wrong. So that is why we now you must remember. And then why do we add like aqueous? We could have had said directly as a water. Here, yes, AlCl3 solid, to this solid we are adding aqueous. Aqueous, yes, only aqueous. So, but we should tell in the equation we are dissolving it. But if you add it as H2O water, there is an issue with balancing it. Now, if you write like this, there are no issue. We don't have an issue. Why? We know we are going to dissolve it. Otherwise, you can't call it as an equation, right? Now it's over. That is why we are putting it as aqueous. Keep that in mind. Okay. And remember, standard enthalpy of solution. Now, enthalpy of solution can either be birds. I can hear some chirping. So either be endothermic. We have birds in at home. Next to what? Balcony. Yeah. Endothermic or exothermic. I think in Gujarat, you guys have a lot of wildlife, right? So I think it's you guys have a reserve or something. I think like a huge reserve of like lot of you're locking away, right? You can have many safari, all the lions. Few lions are also there, I guess, right? Endangered. Have you seen Gujarat lions? Oh my god! But you had been in Sri Lanka, right? I guess for the. Okay, Buddha, right. Endothermic or exothermic. It can either be endothermic or exothermic. So that is what we are going to learn, right? So the basic guideline is now the enthalpy of hydration. Right? It could be endothermic or exothermic. Now, most of the time, students are getting confused between enthalpy of what? Hydration and enthalpy of solution. Now, you tell me now, if you have heard about it before, what is the difference between enthalpy of hydration and enthalpy of solution? In many cases, students are getting it what? Kind of confused, right? So, sometimes they may write the definition They may think it's the same thing. They don't see clear the difference between them. So what is the difference between them? Enthalpy of solution and enthalpy of hydration. Looks similar but not the same. Yeah. Okay, then fine. Then I will write the equation and you should tell me the difference. That would be much better. You tell me. Tell me the difference. Enthalpy of hydration, and I want you to come up with a definition for it. Enthalpy of hydration. So just like for everything, for standard enthalpy of hydration, for standard enthalpy, you need H note here, HYD, right? I will write a standard enthalpy of hydration for magnesium. You tell me the difference, right? Magnesium 2 plus aqueous. Hmm? Tell me, analyze and tell me what is the difference you see between these. Yeah, still it is ionic product. What about the state here? The state of the reactor. It's a gaseous ion, just like the um, standard lattice enthalpy we discussed. We talked about ions getting dissolved, forming a lattice. Write the definition for this. People. Yeah, impressive, right? Enthalpy change when one mole of a gaseous ionic substance dissolved in sufficient water to form a infinite dilute solution of aqueous ions, right? Much preferred, right? Aqueous ions. Oh, your definition is also okay, fine, but it is more clear. Infinite dilute aqueous ions. Infinite dilute solution is also fine, fine, good. Now, nothing. Now you have understood the difference between them. Otherwise, you will always make that error. Even when I was at QA, even I was making that error. Hydration and solution always. Even now, when I am thinking about it, I just take a minute and think, okay, whether I am talking about hydration or solution. It looks similar, right? Uh, Now, what about this one? Is it endothermic or exothermic for this one? It is always exothermic. Why? These gaseous ions can be dissolved quite easily. It is anyways getting dissolved. All I told you, it could be endothermic or exothermic. It depends, right? It depends on the compound, right? Sometimes for some compounds it is endothermic, for some compound it is exothermic. For compounds that are getting dissolved easily, like some compounds, it is exothermic. For some compound, it is exothermic. You can't know it. You just have to do it and think. You have to do the experiment and then only you can tell whether it is endothermic or exothermic. There's no way to know whether it is endo or exo. Right? But for this one, definitely exothermic. Likewise, for some enthalpies, some definition of enthalpies are always exothermic, some are always endothermic, some are you can't decide on that. Okay, I think you can you read what I'm writing on the screen? Is it readable? Okay, good. Because I'm writing compound interest. Right. Um, Now with the diagram, actually we can explain. Can you tell me then why it is always exothermic? Why is that? Enthalpy of hydration. Why? What? It is a gas, right? And with a diagram we can explain, right? Now since it's a gas, now this is the gas. Now we are going to dissolve it, right? Let's say potassium ions. It is in gas state, right? So now we are putting it to water, and water. These are the water molecules. Getting dissolved means chemically intermolecular interactions are being formed, right? Now remember, between water molecules we have hydrogen bonds, right? If a ion, right? If a solid is getting dissolved, between these particles and the water, intermolecular interactions are happening. I'm talking about intermolecular interactions, right? Not intra. I'm not talking about covalent bonds, ionic bonds, but I'm talking about intermolecular interactions. I'm talking about what? London dispersion forces, uh, dipole-dipole interactions, permanent dipole interactions, induced dipole, instantaneous dipole interactions. Those are the intermolecular interactions. Now here we have ion, potassium plus ion. So between this and the now we have this water molecule. It is polar, right? It has a polar bond. It is here. It is what, delta minus, delta plus. Right? So therefore, it is polar. This is highly polar. This is partial polar, right? There's a partial polarity. That is why we call delta minus. This is an ion. It is completely polar. Very attractive, completely polar. In the gaseous state, it is more polar compared to an ion in a solid or a liquid, right? Very strong ionic polarity is there in this ion. So therefore, the moment you put it into water, it is forming this stronger. We call them as what? Ion dipole bonds. This is the dipole. This is the ion. No, it doesn't break. Why? This is a covalent bond. You can't break a covalent bond. This covalent bond is what? It's a intermolecular interactions. You can't break this with a intermolecular interactions. Usually you can't. Very difficult. Right? This is very stronger. But compared to other intermolecular interactions, right? This is very stronger. Hydrogen bonds, London dispersion forces, right? Permanent dipole interactions. Compared to them, this bond is very strong. Iron dipole interactions. This is very strong, but not with this. You can't break this covalent bond with that, right? There are exceptions. There are exceptions with with some experimental conditions, control conditions. You can break even a covalent bond, but here you can't break with this, right? So we call it what as ion between an ion and a permanent dipole. Ion dipole bond, not just one. This ion is surrounded by, right, just like a what? Um, like when you put some food to a set of stray dogs or a set of lions in Gujarat, you throw a piece of what? A chicken leg. So it is getting surrounded. These are like hungry sharks, right? So just imagine this is happening, right? This molecule, that is how they behave. It is what? Yeah. Okay, so if let's take a hungry shark and a piece of chicken. So the potassium plus is the piece of chicken leg, and this whole molecule is like a hungry shark, but the oxygen is the mouth of the, because this is where the polarity delta minus. It is always between a delta minus and a plus, right? See, not between hydrogen and helium. Keep that in mind. Very good question. It is always between the delta plus and the delta minus and the negative positive charge. Delta plus, delta minus. Always between this. It is getting surrounded. Remember, these are what? Spherical. This is not just a circle, spherical. So around it, just like around a football, from everywhere, from the bottom, from the top, three-dimensionally, it is getting surrounded by these hungry sharks, right? Not just one molecule, everywhere it is getting surrounded. More bonds formed, more energy is released. So it is exothermic. Now you can right. Okay. Now this is enthalpy hydration, right? When you form this, energy is released, exothermic. Now we are talking about enthalpy of hydration. Now then after that I will show you enthalpy of what? Solution. Why it can be either negative or positive. I'll show you that too. So it is getting surrounded. Before this, you have a additional step for that. That is why it can be either endothermic or exothermic. Right? Okay. Right now, this is in the gaseous state, you are dissolving it. Now, if it is the enthalpy of hydration, then what is enthalpy of solvation? It is actually you have a ionic solid plus and the minus. Minuses are larger, right? Here minus, here's a plus. And here minus. My diagram is not that clear, right? It should be like this actually. Right? Nearby you don't have negatives. But let's take a small, take it for an example here. So this is the ionic lattice. This is a solid. You are adding aqueous and you are dissolving it, right? And once you dissolve it, these ions are surrounded by water molecules, right? Just like in a hydration enthalpy. Same product, right? But product is the same. You have the positive ions and negative ions. Just imagine, right? And just like hungry sharks, these are getting surrounded by water molecules, right? This is other way. This is the other way around, right? Hydrogens are what? This is to put the title as just an the diagram explanation. This is for enthalpy of a solution. I haven't shown you how it is happening in enthalpy of solution the previous one. Right? In enthalpy of solution, now again these water molecules are surrounding it other way around. Oxygen to the side of cations, hydrogen to the side of just like this, they are getting surrounded. Right? Now for this to happen, first of all, you should be able to break the solid. Previously, we are directly adding H plus gaseous ions into the aqueous medium. Here, first of all, you should be able to break the lattice. You need to break the lattice, and then only this is forming these bonds. Right? When these bonds are formed, uh, um, uh, ion dipole interactions. Before this is formed, when this is forming, energy is released. Energy released, right? But before that, you should be able to break the lattice. You need to break it, right? Understood? Hello? You should be listen, na? You should be able to break it. To break the lattice, what do you need? Energy. That energy must be taken from the surroundings, right? Surrounding means the energy here released is used to break the lattice. Now you may ask the question, right? Very interesting one. Now, to break the lattice, right? This so for breaking is what endothermic, absorb energy, right? To break the lattice, they are absorbing energy from the energy released. Now, which happened? Yeah, so to breaking is endothermic, dissolving is exothermic. Now, energy from the dissolving is used to break the lattice, right? But when you look at the sequence, which happens first? First one or second one? Endothermic. So for this to happen, first of all, yeah, endo no. So you may ask a question, now how can that happen then? Because this thing has not happened yet. And I am telling you, this energy is used to break the lattice, right? To absorb this energy, the second phase has not happened, right? Is it? Then how can that happen? That is the reason why atoms and molecules and electrons are behaving very differently than than we can think of it, right? That is why there's a specific branch of physics. Once you are in the university, when you are doing a master's or PhD, if you are willing to do it, right? So the atoms and molecules and electrons and protons are not behaving in the environment that we are living in. They are living in a multi-dimension. They can even go back and forth with time. Only with quantum mechanics we can explain. Maybe the because for this to happen, first of all, this should have happened, right? Second phase. But when you look at it theoretically, the second one, the energy of the second phase is absorbed to break the lattice. How can that happen? The first one happens first, second one happens later. So it means we cannot explain with the normal Newtonian physics, right? So it must be something to do with time, right? Who knows? These atoms and molecules are moving back and forth in time. Maybe that is the explanation why it happens like that. That is why for atoms and molecules and electrons, there is a special branch in physics, quantum mechanics, string theory, unified field theory, because it works in a different way. They go back and forth in time. That could be the reason. I don't. Maybe who knows, right? Maybe the quantum mechanics could be able to explain why it is happening like this, right? Okay. Otherwise, yeah, in our usual consciousness, you can't explain this. But remember, if the lattice energy, right? If this lattice is more stronger, lattice is more stronger. Some lattices are more stronger. Lattice more stronger than the energy that is released from getting dissolved here. Energy released from getting dissolved, released by dissolving. Then if the lattice is stronger than the energy release, Is it endothermic or exothermic? If the lattice is stronger, endothermic, right? You got to need more energy. Well, lattice is stronger. Lattice require more energy. Then it is endothermic. If it is other way around, if the lattice is less stronger, very good. If the lattice is less stronger, lattice energy, lattice strength, I would say. Lattice is strong, strength is less than the energy released here. Then in that case, there's excess energy, right? Then it is exothermic. So that is why I'm telling you, depends on some compounds. So you can't predict it, right? You can predict it. You can check whether the energy is sufficient. So depends on the lattice. We can decide whether it is endothermic or exothermic. Okay, right. Simple as that. Now I am going to give you a small task. Sure, sure, sure. Okay, bye bye. Until